Hey everyone. Today we start our study of the most central concept of probability, the concept of a random variable. A random variable is just a numeric expression of an experiment. Very often, the true result of the experiment that we're interested in is a number. For example, the value of the stock 1 year from now, the age of a given fossil, the delay of a flight. That number is called a random variable. Let's look at a specific example. Let's flip 3 coins at random and observe the number of heads. There are 8 possible outcomes in this experiment. All tails, 2 tails and then the head, tail, then a head, then a tail, and so on. The set of all possible outcomes is the sample space. But we are not so much interested in which individual outcome we flip, but we're interested in the number of heads that we obtain. For instance, if we flip all tails, then the number of heads is 0. And if we flip tail, tail, and a head, the number of heads is 1. And here the number of heads is 2, and so on. In other words, we assign a number, the number of heads, to each outcome. For an outcome S, let's call this number x of S. Any such assignment is called a random variable, x. Formally, a random variable x is an assignment or a function on the sample space. X takes an input from the sample space and returns an output in the reals, a real number. Here is one example of such function. Here are more examples. X can be the age of a randomly chosen person in a given class. Our experiment here is to pick a random person from the class and assign that person his or her age. So the outcomes of this experiment are individual people. For example, Xavier, Taiko, Chi, Ella, and so on. The random variable x assigns the age to each person. For instance, maybe Xavier is 20 years old and Taiko is 19 years old and she is 21, Ella is 24, and so on. This assignment, x, is a random variable. Another example. Let x be the number of enrolled students at the University of California next year. Here it is difficult to describe the sample space. Another example is the number of spam calls on your phone next month. Again, it's not clear what the sample space here is. It's probably the space of all possible decisions of the spam callers. I do not know. It is a common situation that the sample space is hard to describe, but a random variable is simple to describe. For that reason, from now on, the role of the sample space will be downplayed, and instead, random variables will take the central stage. Another example is the delay of a future flight, or the age of a fossil, or an imperfect measurement of the distance to some star. The age of a fossil and the distance to some star are deterministic, but because of the imperfection of measurement and because our incomplete belief of the measurement of the age, we model them as random quantities. Some random variables can take on only finitely many values. For example, the number of heads can take on only 4 possible values, 0, 1, 2, and 3. Some other random variables can take on a continuum of values, such as the age of a fossil or delay of a future flight. In this course, we will first study discrete random variables, those that take on finitely many values, or maybe countably many values. So a random variable x is called a discrete random variable if, as a function, it takes on a finite or countable number of values. x1, x2, x3, and so on. If I have an experiment that produces some numbers, what is the first question you can ask? The basic question is, what are these numbers and what are their probabilities? For instance, what is the probability that the fossil is older than 200 million years? What's the probability that you get at most 10 spam calls? What is the probability that the number of enrolled students next year will be larger than 20,000, in which case we'll have to build some new dorms, for instance? All these questions are about two things: what values the random variable can take and with what probabilities. The knowledge of the values and their probabilities of a random variable is called the distribution. If x is a discrete random variable, such as this one, then we can explicitly write down all these values and we can compute the probabilities. For instance, the probability that a randomly chosen person in this class is 21 years old. This is called the probability mass function. The probability mass function, abbreviated PMF, of x is just answering the question, what is the probability that the random variable x takes a specific given value? You give me any value, such as 20, and I will respond, what's the probability that a randomly chosen person in this class will be 20 years old? That probability is P of x. More rigorously, this event is a set of all outcomes, little s, in the sample space, for which the value of the random variable equals x. From now on, we will be downplaying the role of the sample space. And so we will often skip s from the notation, skipping this and skipping this. If you ever get confused about notation like this, you should remember that the rigorous meaning of it is this event. Let's look at the example where the random variable x is the number of heads in 3 coin flips. We considered this example here, and I will move it to this page. What's P of 0? The probability that the number of heads is 0. There is only one outcome in 8 where the number of heads is 0. So this probability is 1 over 8. What's P of 1? The probability that x, the number of heads, is 1. There are 3 outcomes out of 8 possible outcomes where the number of heads is 1. So the probability of that is 3/8. Similarly, the probability that the number of heads is 2 is also 3 over 8. And the probability that the number of heads is 3 is just 1 outcome divided by 8. Our random variable x can only take these values, 0, 1, 2, and 3. The probability that x takes any other value is 0. And so everywhere else, P of x is 0. So we can write this function as follows: 1/8 if x is 0, 3/8 if x is 1 or 2, 1/8 if x is 3, and 0 elsewhere. The graph of the probability mass function then looks like this: 1/8, 3/8, 3/8, and 1/8. And it's 0 everywhere else. A simple property of the probability mass function is that the sum of all the values is always 1. If the random variable takes on values x1, x2, and so on, then the sum of P of xi is 1. To see this, just remember the definition of the probability mass function. It is the probability that x takes value xi. X can only take these values. For this part of the sample space, x takes value x1. For this takes value x2. This takes value x3, and so on. The sample space is a union of mutually exclusive events. And by the additivity axiom, the probability of S is the sum of their probabilities. Probability of the sample space is 1. And so we prove the proposition. For instance, let's sum the values in this example. 1/8 plus 3/8 for x equal 1 plus 3/8 for x equal 2, plus 1/8 equals 1. Let's look at a more general example where we have n flips, and we're looking at the number of heads. What is the sample space? Just like here, every outcome can be expressed as a n-letter word with letters H and T. How many such words do we have? Any letter can be chosen in two ways. So by the multiplication principle, it's 2 times 2 times 2, which is 2 to the n. Because the coin is fair, we have a uniform probability on S. Any outcome is equally likely. Let's compute the probability mass function of this random variable. P of k is the probability that x equals k, which means that we have k heads in n coin flips. Because this is a uniform probability, the probability is a ratio of the number of all n-letter words with k heads divided by the number of all possible outcomes, which is 2 to the n. Now, how many words are there with n letters, of which k are heads? To describe such a word, we just need to choose which letters are the heads. The other letters will automatically be tails. And how many ways are there to choose k positions out of n positions? There are n, choose k. So we computed the probability mass function for the number of heads in n coin flips. Here, k, the possible number of heads, can be anything from 0 up to all heads, n of them. If you graph this function, you will see a beautiful pattern. The function p of k follows a beautiful curve, and that curve is a bell-shaped curve. But why is that so? We will learn eventually. Stay with me. Have a good day.